Hi everyone, and welcome to a Tech Talk video at Eric's Electronics Workbench. So measuring current can be done in two basic ways. The first way is to use a series connected shunt resistance and measure the voltage drop on the shunt. Knowing the shunt resistance and the voltage across it will tell us the current using Ohm's law. That's exactly how a digital multimeter is able to measure current. Then the second way is that you can inductively sense the current flow using the fact that a current-carrying conductor produces circular magnetic fields around it. So of course, the higher the current flow, the stronger the magnetic field. So that's exactly how something like a clamp meter is able to detect current flow. So let's take a look at the 5 ways that you can measure current based on these two principles and some pros and cons of each. So one way to take a current measurement is to use a digital multimeter with a current measuring function built in. Now most digital multimeters can measure both DC and AC amps, but a meter like this Simpson 260 can only measure DC amps. Now these meters have an internal shunt to take the current measurement, and that means you have to break into the circuit for the current measurement as the meter is going to be in series with the circuit. Now you can expect extremely accurate results when using a quality meter, and digital multimeters are very good for measuring low currents down to microamps or even lower, such as picoamps on some meters. But most meters are limited to 10 amps maximum, so if you're going to measure over 10 amps, a different technique is needed to measure current. Now there's some voltage drop on the meter's internal shunt, and the shunt adds circuit series resistance, but it's negligible in most cases. And the shunt resistance goes up as the current measuring ranges go lower. We'll take a closer look at that in just a moment on the Simpson 260. As a quick example on how to measure current with a digital multimeter, I'll use this Fluke 85.3, and let's say we want to measure current in this circuit right here. I'm just going to turn off this electronic load for just a second. So you have to break the circuit, and the meter needs to be put in series with the circuit. Now the correct polarity on these test probes is to take the positive test probe and connect it to the positive side of the power supply, like so. And then the other side goes to the negative, just like so. And this is more negative than this side right here because this side goes around through the circuit, in this case the electronic load, and then returns out to the power supply's negative. If you reverse the polarity of these test probes, you'll end up getting a negative symbol on the display. The actual current measurement won't be affected. But if you're concerned about showing positive or negative current flow and you want that display to be correct, then again, this is the correct polarity on the test probes. All right. And also, if you don't know the current level that you're going to measure and not exactly sure, how much current is going to flow, always start with the highest current measurement settings on your meter. So in this case, on the amps setting, from amps to common is fused at 10 amps, and from milliamps and microamps jack right here over to common is fused at just 400 milliamps. So again, choose the appropriate range. I have it set here on the 10 amp setting, of course, and then over here it's on the milliamp and amp setting, not microamps. So if this is set to the wrong position, you'll just get an overload indication. It won't actually hurt the meter, but it will blow the fuse if you have this on the wrong setting here, into the wrong jack, and too much current flows. Okay, so I'll turn this back on again. So you can see 1.5 amps right there, and 1500 milliamps or 1.5 amps. So perfect, just that simple to measure current. So let's take a look at the current shunt resistance in the Simpson 260. So I'll turn this back off. Disconnect these probes. Move this out of the way. I'm just going to turn off the electronic load. Set this down here. Something else that's a good practice to get into is when you're done measuring current, return the test leads back over to the volt-ohm diode setting, like so. So I'll move this over like that, and then continue on using the meter. The reason that this is good to just leave the probes over on the volt and ohm setting over here is because this is essentially a short circuit between amps and common. So if this test probe is over here in the amp setting, you grab your test probes and you go to take a voltage reading, you have a direct short across these test probes. So again, good idea to always return them over to the voltage setting. You're more likely to take a voltage measurement or maybe a resistance measurement than you are probably current anyways. And if you set this on this meter anyways to voltage or one of the other functions, and this probe is over here in the amp setting, the meter will beep as a reminder that this is in the wrong setting. Okay, so let's take a look at the shunt resistance in this meter. So it's set to 500 milliamps right now. So of course this is, again, is on the resistance setting. If I touch the probes together, it falls down to a very low value. So I'm just going to probe in here to the jacks on the front panel right there. As you can see on 500 milliamps, it's measuring 1 ohm, right? So that's the internal shunt resistance on the Simpson 260. Now if I go to 100 milliamps, now it's 3 ohms. So you can see as the current ranges are going smaller and smaller, the shunt resistance is rising. If I go to 10 milliamps, now it's 25.5 ohms. So that's a noticeable amount of resistance. If I go to 1 milliamp, you can see the meter is indicating, maybe a little bit of glare on the screen right there. See how it's come up a little bit? So that's measuring the current that's actually flowing out of this meter for the resistance measurement. But now in the 1 milliamp setting, see it's 254.1 ohms, 0.2 ohms, but basically 254 ohms, much higher than we saw on 500 milliamps. And the reason is because in this meter, it's a passive design, and it needs to have voltage drop across the shunt to have enough voltage to drive the meter. There's no amplification, no active circuitry in a meter like this. So to get enough voltage drop, you have to have a large enough resistance because 1 milliamp is a very, very low current. So if you only had 1 milliamp flowing through the low resistances that we saw in these other ranges, you wouldn't develop enough voltage drop on those shunts to have any meaningful reading. And the same thing is true on a digital multimeter. Although there's active circuitry in a meter like this, you have a higher shunt resistance between this milliamp microamp jack over here than you do on the amps jack between amps and common versus the milliamp and microamp. So again, same holds true on this meter as it does on an old style meter like this. And the Simpson 260 does have the ability to measure 10 amps. And if we go, the 10 amp setting is actually from this jack right here over to this jack right there. I believe it's supposed to be in that position right there, although it shouldn't really make a difference for this measurement. But if I go across those two jacks, you can see the resistance is extremely low. In fact, it says 0.2 ohms right there, which basically looks the same as if I just touched these probes together. So really, this shunt that's in here on the 10 amp setting is extremely low value. It basically looks like just a heavy gauge piece of wire between the two jacks, but it is a very precision resistance, but it's just a fraction of an ohm. So you'd have to have a different meter to even read that value. So another way to measure current is with a current shunt and a voltmeter. And that's exactly what I have set up here. So this is the current shunt, and now the Fluke 85.3 is set to measure millivolts DC. So this is essentially what was going on inside this meter, but there are advantages by having the external shunt. So the shunt will work on both AC and DC amps. So this device here doesn't care whether it's AC or DC that you're trying to measure. But you do have to have an appropriate voltmeter to measure the voltage that this shunt is creating. So you can see it's a very small value, just 2 millivolts. So of course the meter needs to be able to detect that. And if you're measuring DC current, then this is measuring DC volts. If this is AC current, then you're measuring AC volts. So depending on the shunt resistance, it can be made for extremely low or up to extremely high currents. Now again, like before with the digital multimeter's internal shunt, with this system you have to physically break into the circuit for the measurement. That's exactly how I have things set up here, and I'll just explain that in just a moment. And the accuracy depends on the shunt resistance tolerance and the tolerance of the voltmeter being used. And there is some voltage drop on the shunt necessarily, and the shunt adds circuit series resistance, but it's negligible in most cases. And as before with the digital multimeter and the analog meter, the Simpson 260, the shunt resistance goes up as the current measuring ranges go lower. Now this whole system can be made passive by using an analog meter. Then the whole system is just self-contained, and it's basically just being powered off of the circuit that it's measuring. And a shunt like this is often used in more permanent installations. I have this set up with these test leads, and I do use this on the bench. This is a 100 amp shunt, very convenient to use when I need to measure higher currents than something like the Fluke 85.3 is able to measure. It's very handy because these leads right here just go over, they have these banana plugs on the end, they plug right into the meter, and you basically convert the meter from 10 amps over to 100 amps. But a shunt like this, of course, is meant to be panel mounted or chassis mounted in a more permanent installation as well. So the setup that's going right here, we have the positive from the power supply. It's coming over through the shunt. The shunt is a very low resistance. It comes out of the shunt on this wire right here, this lead, comes over to the electronic load, returns from the electronic load on the other side on the negative, right here back to the power supply. So basically the same setup as we were using with the digital multimeter. We're measuring current, except now the shunt is measuring the current, and a voltage is being created across this shunt resistance that's on these two leads right here. They're going into the meter, and you can see it's measuring 2 millivolts. Now this particular shunt is rated up to 100 amps, and it creates 1 millivolt per amp. So you can see I have this set to 2 amps, so 1.998, so right at 2 amps, and 2 millivolts. Makes sense because 1 millivolt per amp. So you just have to do the conversion, and you can basically read the current directly right off the display. So another way to measure current is with an induction ammeter, and that's exactly what this meter is right here. So you can see the center scale sits at 0, and then the left and right scales go up to 100 amps. So an induction ammeter works by sensing the magnetic field around the conductor. It's really only meant for DC current. So AC current would try to swing the needle in both directions, and effectively it would just remain centered. Now if the AC frequency was extremely low, maybe only a few hertz, the needle probably would track back and forth, but again, these are meant for DC current. And these induction ammeters are extremely easy to use because to use them, you just place the wire that you want to measure in this channel on the back. So a big advantage of the induction ammeter is that it doesn't require breaking into the circuit. Now the accuracy on these types of meters is typically lower than other methods, and insulation thickness can affect the accuracy, and I'll show you that in just a moment. And these are best for higher current levels, really limited only by the range of the meter scale. And of course, you're not going to be measuring down into the microamp range with a meter like this. And these are a passive design, so they don't require any kind of power like a battery or something like that. It's basically powered off the magnetic field around the wire. So I'll turn the electronic load on, and you can see it's drawing 15 amps right now. So if I take the meter and just place it against the wire right there, you can see it is indicating. Now this meter is quite old and it's not all that accurate. It's actually closer to 25 amps that it's trying to show right there. And it's really just a 15 amp current that it's measuring, maybe just a little bit under 25 amps. So again, this meter it's pretty old. It's been around for many, many years. But it's just that simple. Just take the wire, place it in that channel, and it indicates. But it doesn't take much distance away from the wire. You know, as I start to move that, see how the needle goes back towards 0? So imagine if this wire had very thick insulation on it. Effectively, that's moving it out away, and it does affect the accuracy quite a bit. Now notice it's deflecting to the right-hand side. If I go to the other positive wire right there, you can see it moves over to the left-hand side. So that's why the scale goes both directions. Turn the electronic load off again. So just that simple to use those meters. Just place them against the wire and you're able to take a current reading. And they're often used in automotive applications. You can see on here it says alternator current indicator. They do make induction ammeters that go to very high current ranges that can be used to measure starter current motor draw and things like that. So current clamps are another way to take a current measurement. I have 3 different examples here. So current clamps work by sensing the magnetic field around the conductor, and they're extremely easy to use because they don't require breaking into the circuit like we did with the current shunt to take the measurement. So take the current clamp, just open the jaws of the clamp, put the conductor into the center, close the jaws, you're able to take the current measurement, just that simple. Now some types of current clamps are AC current only, and they essentially work by using the current transformer principle, but other types are AC and DC current, and they use a Hall effect sensor to detect the current flow. So this current clamp right here is AC current only, this is AC and DC, and this current clamp is AC and DC. Now the Hall effect sensor requires power, usually batteries inside the current clamp. So there's batteries inside this current clamp, and you can see the power on indicator light right there. And of course this clamp has batteries in it as well. There's a number of other features in this clamp and a display, but of course that Hall effect sensor requires power. Now in the DC current mode, the Hall effect sensor requires zeroing before you take the measurement. So on this current clamp there's a 0 adjust right here. On this current clamp there's a 0 setting right here. If you don't zero the clamp, you'll have an offset voltage that would interfere with the measurement you're trying to take. But in the AC current mode on these clamps, the 0 adjust is not necessary, and there's no zeroing on a clamp like this. Now the AC current frequency needs to be within the range of the clamp. So on a clamp like this model, for example, it's a Fluke 80i 1000S. The frequency range is 5 Hertz to 100 kilohertz, so quite a wide frequency range. But of course you need to be within the frequency range no matter what it is on the clamps. If you're outside the frequency range, then they'll just end up dropping off and not have the correct response. Now the accuracy on current clamps is extremely good, but some current clamps require an external digital multimeter if it's not built in. So on this Fluke 355, of course, the display is built in, all self-contained, but for this current clamp and this one, they're going to require an external meter. You can see this one here, the Fluke i410 is plugged into this Fluke 289, so it's requiring an external meter, and the accuracy is going to be the accuracy of the clamp and the accuracy of the meter that you're using. Now most current clamps are not the best choice for extremely low currents unless the clamp is specifically made to sense in the low milliamps or perhaps microamp range, and such clamps do exist. But they're a very good choice for measuring extremely high currents, and clamps often measure hundreds or thousands of amps. So on this current clamp right here, the Fluke 80i 1000S, the current range goes from 100 milliamps up to 1000 amps, and it has 3 different ranges. There's a little range switch right here to select the range that you want. On this one, the Fluke i410, it goes up to 400 amps, and this Fluke 355 goes to 2000 amps. Now a trick that you can do is to increase the sensitivity of the current clamp by looping the wire through the jaws of the clamp. So as I mentioned, you would open the clamp, you put the wire in here, and it just passes straight through, and that's how they're intended to work normally. But if you take the wire and you add a loop, it will double the reading. We'll take a look at that in just a moment. But you need to use that idea with care because you don't want to overload the current clamp. If you were reading, a very high current and you had looped it once or twice through, several times, it's going to possibly overload the meter if it's a very high current. So just be cautious of that. But that trick works very, very well if you're trying to measure an extremely low current and the clamp is having difficulty detecting it or maybe giving slightly unstable reading. If you loop it and just take that into consideration when you take the actual reading, you can actually increase the sensitivity. So handy little trick to do. So I have an AC power supply connected to this dummy load resistor, and the power supply is set at such a voltage as to have 2 amps flowing through this power resistor. So if we take a measurement right now, like so, and go like this, you can see the glare off the screen. There it is. So 2 amps. So just that simple. Wire just goes right through the current clamp and you get the reading. And if I go like this clamp right here, you can see it says 2 point and some change right there, but millivolts AC. So on this current clamp, the output is rated 1 millivolt per amp. So knowing that that's the ratio or the reading that you're going to get, you just use that factor when you're taking the reading here, and you can read directly, even though this is millivolts AC, you're reading it as amps. So 2 millivolts means 2 amps. So I'm going to disconnect this lead right here and back to this clamp right here, and again just loop it through like so, and go back over and move this here just a little bit. Connection over here again. So actually I doubled it up right there, so now you can see it's actually reading 4 amps right there. So it's passing through twice, so it was 2 amps, but when it passes through the current clamp jaws twice, doubles the current reading. So here's several things to remember when using a current clamp. So if I take this clamp and go around the red test lead like so, you can see it's measuring 2 amps AC. So it doesn't matter if the current clamp is facing this direction on the wire or if I go this direction on the wire, it's still the same displayed reading, and there's no displayed polarity because it's AC current. Now imagine if this is measuring DC current. If you have the clamp facing this direction on the wire or you go this direction on the wire, it will make a difference on the displayed polarity. So in one direction you'll have a negative symbol on the display. Now if I go back around the red test lead like so, you can see it's 2 amps. And of course I can go to this black test lead and get the exact same reading, which of course makes sense because these are coming from my power supply. They're just going over to this resistor, so the current flowing at this point has to be the same as the current flowing at this point. However, if I take both wires together and go through the current clamp, now you can see it essentially just falls to 0. So that's important to remember because imagine if these 2 wires were actually inside a power cord. Well, you couldn't measure the power cord by just clamping around the cord and taking a reading. You would need to break the wires out of the power cord and then just pick one of the wires and take the current reading on just one wire. Now the reason that the wires can't both be through the clamp at the same time is because when the current is flowing this direction on the red wire, it's going this direction on the black wire because it's AC current, it's alternating back and forth. And the same thing would happen with DC current. If it's flowing in one direction on one wire, it's going the other direction on the other, and they just essentially cancel out in the current clamp. Now something else is that when you're taking a measurement, you don't want the current clamp to be apart at all. It has to be completely together. So if I go like this again, and see the 2 amps, but as I start to open up the clamp just the tiniest amount, you can see the current falls away. The numbers are no longer accurate. So it's very important that those be completely closed. That might seem like an obvious sort of a thing, but if this is in an awkward position, you're trying to reach in, in some way that the wiring is maybe kind of stiff and you're trying to get the, jaws of the clamp around some awkward location, sometimes it can hang up a little bit and they'll be open just slightly, and of course that will affect the reading. Now on a current clamp like this Fluke i410, it can measure both AC and DC current, but it requires an external digital multimeter to take the reading. And if you're measuring AC current, then this needs to be set to AC volts, or millivolts for that matter. And if you're measuring DC current, then this needs to be on DC millivolts. So basically the signal that's coming out of here is either AC voltage or DC voltage, depending on the current that you're measuring. There's no switch to select between AC and DC. It's just up to you to know which way, or which type of current you're measuring, and then, make sure to have the meter selected appropriately. So as the last example of a way to measure current, let's take a look at the current transformer. Now, I already mentioned that some current clamps are based on the current transformer principle, but let's take a closer look and see how this device actually functions. So a current transformer operates on the principle of sensing the magnetic field around a conductor, and they can only measure AC current. You cannot measure DC current with a current transformer. And of course, the frequency of the AC current must be within the range of the transformer. Now, all current transformers require that a wire be routed through the window of the transformer. So this hole right here is known as the window. So the wire that you're trying to measure the current on needs to pass through this window. And that, of course, makes the current transformer less than ideal in some applications of trying to, measure the current, because you may not physically be able to move the wiring over to the transformer and, route it through the window. Oftentimes that would be more appropriate to use a current clamp. But current transformers certainly have their place. They're often used in the instrumentation for power generators and situations like that, where you have permanent wiring and, this is panel mounted or chassis mounted. So current transformers offer very good accuracy, and they can measure extremely low current up to very high current depending on the turns ratio. But of course that accuracy is going to depend on the external meter that you use. So for this example, I'll just measure the voltage that this transformer produces with this Fluke 289, but this could be driving an external panel mounted meter or something like that. And if it's used with an analog meter, then the entire setup can be made passive, because the analog meter can derive its voltage off of this current transformer. It requires no other source of power. Now you always need to operate a current transformer with the secondary terminated by a load resistor. Otherwise the transformer can be damaged by high voltage that builds up on the secondary, because it's acting like a step-up transformer. So you can see I have this resistor right here. It's 150 ohms. I have it across the secondary. It's just a random value that I've picked. It should be perfectly fine for this test setup. And this resistor will affect the readings or the calibration that you're getting off of the transformer. So this won't be calibrated. The actual voltage that this develops isn't something that you can just read directly and convert to current, because I have no idea what effect this resistor will have as far as loading down this transformer. So it's very important that this resistor be chosen correctly, and possibly even be an adjustable resistor in the final setup. But let's think about what's actually happening. So the wire that you're passing through the window of the transformer is the primary. So you could think of that as one turn. But in this transformer, there's a toroid in here, and it has hundreds of turns of wire typically, and basically gives you a step-up transformer of 1 to say 500 or 1 to 300 or something. It's a very, very high ratio. So if this isn't loaded by this resistor, you'll get extremely high voltage on these terminals, and it basically will just arc through the insulation on the windings. So let me take my meter, and I'm just going to move this over like so and connect to these terminals here. All right. So this is set to volts AC. I'm going to take this wire right here, and I'll just pass it once through the transformer, and I'll connect it to the power supply. And yes, we do have a reading right there. So let's take a look. This current clamp, so you can see there is 2 amps that it's flowing. So the voltage that's being developed on the secondary with the loading of this resistor, you can see it's 0.630 and some change right there, so about 630 millivolts. So now I'll disconnect the wire from the power supply, and let's route this around. Let's say go once, and again, and again. So now we have 3 passes through the window right there. You can see the 3 wires right there, how they're going through. So now, if we go over here, connect that back again. So again, no change in the current. This wire right here, you can see 2 amps. But now you can see on the voltage over here, definitely a higher reading. And that's the effect that I was mentioning on the current clamp as well. If you loop the wire multiple times through the jaws of the current clamp, you'll get a higher reading, and it just basically becomes more sensitive. So if this was a very, very low current and you needed to have it more sensitive, you could have multiple turns going through the transformer. So thank you for watching this Tech Talk video. And if you enjoyed this video and found it helpful, please give it a thumbs up. And if you're enjoying the videos on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. So until next time, as always, take care and goodbye for now.